Hi everybody, welcome back to the channel. In this video we're going to take a look at kind of combining two different sections in our book into one video. This is talking about section 4.5 and 4.6 if you're in my class. And in this we're going to kind of summarize what it looks like to be able to graph a function using all of the tools and tricks that we know about so far using calculus. Or I should say some of the things we need involve calculus and some don't. But we can kind of put everything together now after we've talked about critical points, inflection points, maximums, minimums, increasing and decreasing, and talking about concavity. So I've put a lot of steps here on the front on this first page, and these are directly out of our book that you can see kind of how could you go about graphing a function. Now, if you have a function that is a polynomial, quadratic, cubic, something else that you've seen before, or a function that is exponential, logarithmic, a trig function, you should have a really good idea about how to graph all of those separately on their own. Different kinds of roots, a lot of different types of functions individually you should be able to graph. So really what I'm talking about here is not just graphing one function, but it's kind of graphing a combination of functions, which I guess we can combine together into calling it one function, but usually this is multiple functions or multiple families of functions kind of thrown in together into the same function. Okay, so we're going to go over some of these steps and look at kind of some of the details of how to do these things, and then in the next couple of videos we'll take a look at a couple of examples as well. So the first thing you want to think about here, actually let me point this out at the beginning. I put a little note on here. Notice that the first four steps that we're going to have don't necessarily involve any calculus. They could when we're finding asymptotes, but we can find a lot of asymptotes without using calculus. Thinking about horizontal and vertical asymptotes. So steps number 1 through 4 shouldn't even be new to this class. They should be things that you've definitely seen before. And we're going to start out with talking about finding the domain. That's kind of a first thing, and probably a reason why it's a good thing to think about finding the domain first is because if you remember back to when we talked about what it means for a function to have a derivative, one of the criteria is that the function has to be continuous. And back even further when we talked about what it means for a function to be continuous, you may remember that there are a lot of different types of families of functions that we said are continuous on their domain. So in other words, everywhere the function is defined, it's continuous everywhere at those same points. And so before we even talk about where a function has a derivative, we need to talk about where a function is continuous. Before we talk about where a function is continuous, we need to know what the domain of that function is. So that seems like a pretty good place to start. So first of all, we're going to find the domain, then we're going to find intercepts. That means x and y intercepts. One thing that's helpful is to look at whether the function has any symmetry. Now I will point out that most functions, if you just randomly pick a function, do not necessarily have any kind of symmetry, but it is a good characteristics to be able to look for. And so a couple of different ways to look for symmetry you could think about: is the function an even function? You may remember back that means that we're talking about a function that is symmetric across the y-axis. Or is the function an odd function, which means it's symmetric about the origin? Periodic functions also have certain types of symmetry just because of the repeating behavior. And then step number 4, we're going to find any holes in all asymptotes. We typically tend to think that that relates to rational functions, but again, when we start to combine functions together, or families of functions together, we might have part of our function that looks like a rational function and another part looks like something else. And so we can kind of adopt the ideas of rational functions to talk about a more complicated function. So let's just look at the first 4 steps first of all just for a minute, and then we'll jump into the ones that involve calculus. As just a reminder, I will say none of this should feel new to you. All of this should feel like stuff that you've been able to do. If I told you to go do all these 8 steps for a different type of function, now that we've looked at the last 2 sections in videos talking about increasing and decreasing, local minimum and maximum, and concavity, and critical points and inflection points, you should probably be able to do all 8 of these things if I were to give you a function. So again, there's not really a lot of new material here, but I just want to make sure that you know how to find each of these things when they show up in problems. So first of all, let's look at the domain. So when we're finding a domain, I want you to think about where could we have problems? Where could we have issues with the domain? In other words, what I'm asking you is, when is the domain of a function not all real numbers? And so some things you might come up with is definitely when we have fractions that have something with a variable in the bottom. and that's what we would call a rational function. So rational functions where we have a variable down low, that gives us an issue. Another way we have problems is that we have square roots, or not even square roots. Let me put it like this. I'm going to say the nth root over here, but what's important here is that n gives us a problem if n is even. And so odd numbered roots actually don't give us any issues, because if you think about what the issue is, you're not allowed to have a negative number under a square root or a fourth root or a sixth root or under any even root. But if you have a negative number under a third root or a fifth root, that's actually not a problem. If you take the third root of a negative number, you get a negative number. There's no issues there. So the way we would handle something that's a fraction, we would say set the denominator equal to 0 and solve. The way we would handle a square root or an even numbered root over here is we would take what's under the square root. Like let's say I call it y underneath. I tell you what, maybe not y because we often use y for a variable here. So let me just kind of take whatever the expression is, I'll just call it p. And we would say take p and set it greater than or equal to 0 and solve. And sometimes that's easier than others. If you have a linear function underneath the square root, a little easier to solve for. If you have a polynomial underneath the square root, a little bit tougher to solve for where that's greater than or equal to 0, but that's okay, we can still do that. And I would also point out that we don't always have roots that show up as roots. For example, you know that another way to write the nth root of p is to write it as p to the 1 over n. And so just something to be aware of is if you have a fraction exponent where that fraction exponent has an even number on the bottom, that's also going to be an issue. So something to watch out for. Okay, other areas where we have issues is we also could have logs. And remember that when you have logarithms, you're not allowed to have a negative number inside of a log. So again, let me just call this p inside here. And the idea with a log, you're actually not even allowed to have the log of 0. So here, p is not greater than or equal to 0. Here, p is just greater than 0. So these are some issues of where you could have some domain issues that you need to be careful about. Other ones, this isn't a comprehensive list. There are others as well. Other ones include something like if you have a tangent or a cotangent or a secant or a cosecant. And so just being careful, because remember that those graphs of all four of these have vertical asymptotes in them. They all have places where this function is undefined. So you got to be careful about what values you have there. There are others as well, but this is most of what we've seen so far in our list. Is you got to be mindful about in your situation, do you have a fraction? Do you have an even numbered root somehow? Do you have a log, or do you have these trig functions that work? And you could actually have all of these combined together, and so you got to be careful about what could your domain be, or where could you have issues in your domain. Okay, if we go over to number 2, it says find all intercepts. I hope that one should be straightforward. As a reminder, to find all y-intercepts, this one's a little bit easier. You set x equal to 0, and to find all x-intercepts, you can set y equal to 0 and solve. That you've been doing for quite a while, so that I think should be fairly straightforward. Let's see, question is, number 3 is, does the function have any symmetry? Is the function even or odd? And by the way, now not just even or odd, but neither is a perfectly acceptable answer. Remember I said earlier that symmetry, a function having symmetry, is fairly rare. It doesn't happen a lot, or it's not the norm. And so something you should consider is a function is an even function. Okay, there's my abbreviation for function. An even function if f of negative x is equal to f of x, and an odd function, you have an odd function here if f of negative x is equal to negative f of x. And if neither of those things happen, well, then it also could be neither. So just something to be mindful of. It's not like it's either even or odd. Those are your only two choices. There's a third option there as well. And then, is it periodic? Does it have a repeating behavior? Which usually means you have a trig function showing up to some degree, but just something to be aware of. And then number 4, find any holes and all asymptotes. Again, hopefully remember how to do that. We've seen that a lot in past classes. We've seen that a little bit in this class as well. So a hole is where you have a situation where maybe you have a 0 over 0 on the top and on the bottom at that value. And so you got to actually take the limit like we did with L'Hopital's rule in the last section and figure out what you get. Holes most often show up for us when we're talking about rational functions. And so just be careful. Or if not rational functions where it's a polynomial on top and a polynomial on bottom, at least a rational function that might have some other stuff in it. So remember in the last video we had something like the natural log of x divided by x minus 1. Technically this is not a rational function because it has a natural log of x on the top, but it's a composition of a rational function with a natural log function. So you just got to be careful about where you might have that situation show up as well. Remember that for vertical asymptotes, vertical asymptotes are values that are not in the domain after you've already removed holes. So let's say excluding holes. Again, we should have seen a lot of this before in our past. Remember that horizontal asymptotes are talking about what happens as you take the limit of the function as x goes to infinity, and that's kind of the same thing as well with slant asymptotes. You could have that end behavior idea for either of those. Both are talking about what happens to the function as you take the limit as x goes to infinity. So again, nothing that you shouldn't have already seen, but just a little bit of a recap in this video about a lot of the features of functions. Okay, and so that's kind of 1 through 4, the non-calculus stuff. 5, 6, and 7 should be a lot newer. Those should be things that you've seen a lot of lately. So if we say, how do we find values, intervals of increasing and decreasing, how do you find local maximums and minimums? I will remind you that the structure that we've been using is to start with f, to find f prime, and then when we go and talk about concavity as well, finding f double prime. And what we've done, the structure in this chapter has been plug in values on your number line, find what happens with f prime, and if f prime is increasing, then f is, or I'm sorry, let me rewrite that. If f prime is positive, then f is increasing, and if f prime is negative, then f is decreasing. And so we have an idea of how to find maximums and minimums based on knowing where we go from increasing to decreasing and so on and so forth. We could also be finding f double prime, and as a reminder, where f double prime is positive, f is concave up. Okay, f is concave up, and where f double prime is negative, you have f is concave down. And so remember those inflection points, those are points where your graph of f changes from being concave up to concave down, or vice versa. So all three of these other ones should be really pretty new for you. But the idea here is this: can we take all of these features and be able to graph the function, graph the curve? Really, to be quite honest, without using your calculator, can you graph this by hand, knowing a lot of the different characteristics of this function? And if you know what the asymptotes look like, if you know what the intercepts look like, you know if there's symmetry, you know increasing and decreasing, you know maximums and minimums and concavity, you can kind of put all this together and be able to draw hand draw a graph based on its characteristics and its features. Okay. Now I say this because I know you have your graphing calculator, but your graphing calculator is only as good as the person who's typing it in, and we want to be careful making sure that we actually know how to use our calculator correctly. Otherwise, it doesn't necessarily get everything for us. It doesn't do everything for us. In fact, you can go ahead and type in a function like y equals something on your graphing calculator, but you have to be the one to interpret what's actually happening. Your calculator is not going to point out for you critical points and inflection points and the intercepts. I know you can go find those, but you have to be able to know what you're looking for. And so that's the idea here, is can we put all of this together and figure out what is it that we're looking for, and can we graph a function based on knowing all of these criteria, all of this information. So you could really consider this section to be a summary, or I should say these two sections, a summary of how to graph a function based on everything that we've found so far, either in past classes or now in this class, and kind of putting it all together, not just for one family of functions, but now for combinations of families of functions. Okay, so we're going to have some videos. I think I'm going to have 2 videos here with some examples. Go ahead and check those out next. But for now, hope you've enjoyed.